At 9:38 in the morning on August 17, 1943, Lieutenant Colonel Curtis LeMay stood in the operations room at RAF Molesworth in England and watched as 230 B-17 Flying Fortresses lifted off into the grey dawn. Their target was Schweinfurt, Germany. 5 factories producing nearly 2/3 of Germany's ball bearings. If the raid succeeded, German war production would collapse within months. If it failed, the cost would be measured in hundreds of American lives. LeMay knew the odds. Schweinfurt was deep in German territory, beyond the range of fighter escorts. The bombers would fly alone through 400 miles of hostile airspace, defended by hundreds of Luftwaffe fighters and thousands of anti-aircraft guns. Intelligence estimated losses at 15 to 20%. That meant 30 to 46 aircraft would not return. 400 to 600 men would die, be captured, or go missing. But the target was worth it. Ball bearings were the bottleneck in German war production. Every tank required hundreds of bearings. Every aircraft engine required dozens. Every artillery piece, every truck, every piece of machinery depended on precision ball bearings to function. Destroy Schweinfurt's factories, and Germany's entire war machine would grind to a halt. That was the theory. The reality was more complicated. While American bombers prepared to die over Schweinfurt, American factories in Canton, Ohio were producing something Germany could not match. Tapered roller bearings that worked better than ball bearings for most military applications and did not depend on German technology at all. This is the story of how one German immigrant invented a superior bearing design in 1898, how his company became America's answer to Germany's ball bearing monopoly, and how that obscure mechanical innovation helped win World War II without firing a single shot. Friction is the enemy of all mechanical motion. It transforms kinetic energy into heat, while damaging surfaces and wasting power. For thousands of years, engineers have fought friction with limited success. Bronze bushings, oil-soaked wooden bearings, roller logs under heavy loads. Every solution worked temporarily but wore out quickly under sustained use. The Industrial Revolution made friction intolerable. Steam engines, railroad locomotives, factory machinery, all required continuous motion under heavy loads. Traditional bearings failed within weeks or months. Maintenance consumed enormous resources. Downtime crippled productivity. The machine age demanded better solutions. Ball bearings emerged in the mid-19th century as the first major breakthrough. The principle was elegant. Instead of direct contact between moving surfaces, place hardened steel balls between them. The balls roll rather than slide, dramatically reducing friction. A well-designed ball bearing could reduce friction by 90% compared to a plain bronze bushing. But ball bearings had limitations. They worked excellently for light loads and high speeds. Bicycle wheels, machine tool spindles, electric motors, applications where loads were primarily radial, pushing perpendicular to the shaft. But when loads combined radial and axial components, pushing both perpendicular and parallel to the shaft simultaneously, ball bearings struggled. This was exactly the problem facing wagon and carriage manufacturers in the 1890s. A wagon wheel must support the vehicle's weight, a radial load pushing down on the axle. But when the wagon turns, the wheel also experiences thrust loads pushing sideways against the axle. Ball bearings under these combined loads wore rapidly and failed unpredictably. Henry Timken understood this problem intimately. Born August 16, 1831 in Bremstedt, Kingdom of Hanover, Germany, he immigrated to the United States with his family at age 7. They settled in Missouri, where young Henry apprenticed to a carriage maker at age 16. He learned every aspect of wagon construction, wood selection, metal forging, wheel assembly, and bearing design. By age 24, Timken had established his own carriage factory in St. Louis. He was not content to simply build carriages. He wanted to improve them. In 1877, he patented the Timken buggy spring, an innovative suspension system that provided a smoother ride than conventional leaf springs. The invention was successful. Other manufacturers licensed the design and paid royalties. Timken became wealthy and nationally known. But he kept thinking about friction. Conventional wagon bearings required constant maintenance. They needed frequent greasing. They wore out quickly under heavy loads. They failed without warning, stranding wagons on roads far from repair facilities. There had to be a better solution. Around 1895, Timken began serious experiments with bearing design. He worked with his 2 sons, Howard and William, and a nephew. They studied ball bearings, and identified their fundamental limitation. Ball bearings contact their races at a point. Under load, this point deforms into a tiny ellipse, but the contact area remains minuscule. All the load concentrates on this microscopic area, creating enormous stress. Timken conceived a radical alternative. Instead of balls, use rollers. Not cylindrical rollers, which had been tried before with limited success. Tapered rollers. Cone-shaped rollers arranged at an angle between cone-shaped races. This geometry would fundamentally change how loads were distributed. The mathematics were elegant. A tapered roller contacts its race along a line, not a point. Under load, this line deforms into a narrow rectangle. The contact area is 50 to 100 times larger than a ball bearing of equivalent size. Stress distributes across this larger area, reducing peak stress dramatically. More importantly, the tapered geometry allows the bearing to handle both radial and thrust loads simultaneously. The angle of the taper can be optimized for specific load combinations. On May 1, 1898, Henry Timken received United States Patent No. 603-953 for his tapered roller bearing design. The patent drawings showed a deceptively simple device. Tapered rollers positioned between inner and outer cone-shaped races, held in precise spacing by a cage. The design looked obvious in retrospect, which is the hallmark of truly great inventions. But nobody had thought of it before. Timken immediately recognized the commercial potential. In 1899, he incorporated the Timken Roller Bearing Axle Company in a corner of his St. Louis carriage factory. Initial production was small, a few hundred bearings per month, sold primarily to carriage manufacturers. But performance was extraordinary. Carriages equipped with Timken bearings required less maintenance, lasted longer, and handled better than those with conventional bearings. Word spread through the industry. Orders increased. By 1900, Timken was producing thousands of bearings monthly. The factory in St. Louis became too small. In 1901, Timken made a strategic decision. He relocated the entire operation to Canton, Ohio. The move was calculated. Canton was centrally located between emerging automotive manufacturing centers in Detroit and Cleveland. It was near the steel production centers of Pittsburgh and Youngstown. Rail connections were excellent. Labor was available, and land was cheap. Timken purchased a large plot and built a modern factory designed specifically for bearing production. The timing was perfect. The automobile industry was exploding. In 1900, 8,000 automobiles were produced in the United States. By 1910, that number had reached 181,000. Every automobile required multiple bearings, wheels, transmissions, differentials, drive shafts. The demand seemed unlimited. But Timken faced formidable competition. German companies dominated ball bearing production worldwide. Kugelfischer Georg Schaefer, founded in 1883 in Schweinfurt, Germany, pioneered mass production of precision steel balls using advanced grinding machines. Their bearings set industry standards for quality and precision. Svenska Kulliga Fabriken, known as SKF, founded in Sweden in 1907, rapidly expanded globally through aggressive marketing and technical excellence. By 1908, SKF had branch offices in Germany and France. By 1909, subsidiaries in New York, Britain, Denmark, Norway, Belgium, Holland and Russia. SKF became the world's largest bearing manufacturer, producing hundreds of millions of ball bearings annually. American manufacturers purchasing bearings faced a difficult choice. Buy expensive German or Swedish imports, or use cheaper domestic ball bearings of lower quality. Most chose imports for critical applications. This created strategic vulnerability that would become apparent during wartime. Henry Timken took a different approach. He did not try to compete with German ball bearing manufacturers on their terms. Instead, he focused on applications where tapered rollers outperformed balls: heavy trucks, railroad cars, industrial machinery, agricultural equipment, anywhere loads were heavy and combined radial and thrust forces. The technical advantages were measurable. Load testing demonstrated that a Timken tapered roller bearing could handle 5 times the load of an equivalent-sized ball bearing. Service life was 3 to 5 times longer. Maintenance requirements were lower because tapered rollers could be adjusted to compensate for wear, while ball bearings had to be replaced once worn. Railroad adoption was crucial for Timken's growth. Railroads were the largest consumers of bearings in the early 20th century. A single freight car required dozens of bearings. A locomotive required hundreds. The rail industry was conservative, reluctant to adopt new technologies without extensive testing, but the potential market was enormous. In 1923, Timken convinced the Wheeling and Lake Erie Railroad to test tapered roller bearings on freight car axles. The test ran for 1 year, during which instrumented cars traveled thousands of miles under heavy loads. The results were unambiguous. Timken-equipped cars required 60% less maintenance than those with conventional bearings. Failures dropped to nearly zero. Fuel consumption decreased slightly due to reduced friction. The Wheeling and Lake Erie Railroad ordered Timken bearings for its entire freight car fleet. Other railroads noticed. By 1926, major lines including the Chicago, Milwaukee, St. Paul and Pacific Railroad were specifying Timken bearings for new equipment. High-speed passenger trains like the Burlington Zephyr and Santa Fe Superchief used Timken bearings exclusively. By 1920, the Timken Company was producing 90% of America's tapered roller bearings. The company operated multiple plants. The main facility in Canton, a new plant in Columbus, Ohio, opened in 1920. A Canadian facility opened in 1922. Production capacity exceeded 10 million bearings annually. Henry Timken died on March 16, 1909 in San Diego, California. He was 77 years old. He did not live to see his invention's full impact, but his sons continued building the company with the same engineering rigor and business acumen their father had demonstrated. When World War I began in August 1914, Germany's ball-bearing monopoly became a strategic weapon. The British naval blockade cut German exports. American industry, dependent on German bearings for precision machinery, faced severe shortages. Prices spiked, lead times stretched to months. Factories reduced production or shut down entirely, unable to obtain critical components. Ball bearing manufacturers attempted to expand domestic production but faced technical barriers. Producing precision steel balls required specialized grinding machines, most of which were German-made. The metallurgy was complex. Bearing steel must be extremely hard yet resistant to brittle fracture. Carbon content must be precisely controlled. Heat treatment must produce uniform microstructure. Few American steel makers possessed this expertise. Timken, however, already had production capacity for tapered rollers, a different technology that did not depend on German machinery or metallurgical secrets. More importantly, Timken bearings worked better than ball bearings for most military applications. Trucks, artillery carriages, ammunition carts, all experienced heavy combined loads that favored tapered rollers. The United States military, desperate for reliable bearings, turned to Timken. Orders flooded in, the company expanded rapidly, adding shifts and hiring workers. By war's end in 1918, Timken had supplied millions of bearings for military vehicles and equipment. Performance in combat conditions was excellent. Failure rates were low. Maintenance requirements were minimal. European military observers noticed. British and French procurement officers visited Canton to evaluate Timken's technology. Post-war, several European countries placed orders for tapered roller bearings, breaking German ball-bearing companies' monopoly in their home markets. In 1917, facing steel shortages due to wartime demand, Timken made a strategic decision that would prove crucial 2 decades later. The company began steel production, establishing the Timken Roller Bearing Company Steel Division in Canton. This vertical integration allowed Timken to control bearing steel quality from raw materials through finished products. Making steel in-house provided multiple advantages. Steel composition could be optimized specifically for bearing applications. Carbon content, chromium, molybdenum, and other alloying elements could be adjusted to achieve ideal hardness, toughness, and wear resistance. Heat treatment could be tailored precisely. Quality control was absolute because every step occurred under Timken's supervision. Most importantly, vertical integration eliminated dependence on external steel suppliers. When war came again, Timken would not face shortages or quality problems that plagued competitors relying on commercial steel suppliers already overwhelmed by military demand. The company entered the Great Depression in 1929 with strong fundamentals. Diversification into non-automotive markets, agriculture, industrial machinery, railroad equipment, softened the collapse in automobile production. Timken's financial management was conservative. The company maintained low debt and substantial cash reserves. While competitors failed or merged, Timken survived intact. During the 1930s, Timken expanded into new applications. Marine propeller shafts required bearings capable of handling enormous thrust loads in corrosive saltwater environments. Tapered rollers were ideal. The United States Navy began specifying Timken bearings for destroyer and cruiser propeller shafts. In 1932, Timken developed removable rock drill bits for mining and construction, providing additional markets for steel production during depressed automotive demand. When Howard Timken Sr. died in 1940, his son Howard Timken Jr. became company chairman. The company operated manufacturing facilities in Ohio, Canton, Columbus, Mount Vernon, and internationally in Canada, Britain, France, and South Africa. Employment exceeded 15,000 workers. Annual production exceeded 100 million bearings. Then Germany invaded Poland on September 1, 1939. World War II began. Britain and France declared war on Germany 2 days later. The United States remained officially neutral, but began military rearmament. Orders for military equipment flooded American factories. Timken's production increased immediately. The company opened new facilities across Ohio. The Zanesville plant, opened in 1943, focused exclusively on military bearing production. The Timken Ordnance Company, established in Canton in 1941, manufactured artillery gun tubes, using Timken steel technology. By 1942, when the United States entered the war following Pearl Harbor, Timken was already operating at near maximum capacity. The War Production Board designated bearings as critical strategic materials and allocated Timken's output to military priorities. Automobile production essentially ceased. All bearing production supported the war effort. The statistics were staggering. Every Jeep used 24 Timken tapered roller bearings. Wheels, transmission, transfer case, differentials. The United States produced 660,000 Jeeps during the war. That required 15.8 million bearings for Jeeps alone. 2.5-ton trucks used 48 Timken bearings each. Hundreds of thousands of trucks were produced. Tanks used Timken bearings in tracks, road wheels, bogie wheels, drive sprockets, transmissions, and turret rings. Sherman tanks alone required over 100 bearings per vehicle. Aircraft landing gear used Timken bearings. B-17 Flying Fortresses, B-24 Liberators, B-29 Super Fortresses, all relied on Timken tapered rollers in main landing gear and nose gear. Naval vessels used Timken bearings in propeller shafts, turbine machinery, and gun turrets. Destroyers, cruisers, battleships, aircraft carriers, all specified Timken. The advantage was not merely that Timken bearings were available domestically, eliminating dependence on imports. They often performed better than ball bearings for military applications. Combat vehicles experienced shock loads, vibration, contamination, inadequate maintenance, and extreme temperatures. These conditions destroyed ball bearings rapidly. Tapered rollers survived. Load capacity was critical. Tank tracks generated enormous combined radial and thrust loads as vehicles turned. Ball bearings under such loads failed within dozens of hours. Timken tapered rollers operated for hundreds of hours before requiring maintenance. Durability translated directly into operational availability. Tanks with Timken bearings spent more time in combat and less time in repair depots. Adjustability provided another advantage. Tapered roller bearings can be preloaded by adjusting the position of the inner race relative to the outer race. This eliminates clearance and optimizes load distribution across all rollers. As wear occurs, the bearing can be readjusted to maintain performance. Ball bearings have fixed clearances determined during manufacturing. Once worn, they must be replaced entirely. Maintenance was simpler. Field mechanics could adjust Timken bearings with basic tools, wrenches and feeler gauges. No precision measuring equipment required. This was crucial in combat zones where sophisticated tools were unavailable. Ball bearing replacement required removing entire assemblies, a time-consuming process requiring specialized equipment. Manufacturing scalability was decisive. Timken's vertically integrated production model allowed rapid expansion without dependence on outside suppliers. The company produced its own steel. It manufactured its own machining tools. It controlled every step from raw materials to finished bearings. When production needed to double, Timken simply added shifts and hired workers. No bottlenecks, no supplier delays. By 1943, Timken was producing bearings at rates that would have seemed impossible 5 years earlier. The company operated 24 hours daily, 7 days weekly. Women replaced men drafted into military service. Training programs converted inexperienced workers into skilled machinists within weeks. Quality control remained stringent, despite production pressure. Defective bearings were rejected regardless of quotas. Meanwhile, in Germany, Albert Speer, armaments minister, faced a crisis. German war production depended on ball bearings manufactured primarily in Schweinfurt. 5 factories in that city produced approximately half of Germany's total ball bearing output. Kogel Fischer George Schaefer, the largest complex, employed 11,700 workers. VKF, Vereinigte Kogel Akkor Fabriken, operated 2 plants. Fichtel and Sachs produced specialized bearings. Combined output was approximately 140 tons monthly. Allied intelligence identified ball bearings as Germany's most critical vulnerability. Destroy Schweinfurt, and German tank production would collapse within months. Aircraft engine production would halt. Artillery piece manufacturing would stop. The entire German war machine would grind to a standstill. That was the theory tested on August 17, 1943. At 0940 hours, Lieutenant Colonel Curtis LeMay received confirmation that all aircraft were airborne. 230 B-17 sailed, heading toward Schweinfurt. Another 146 heading toward Messerschmitt factories at Regensburg. The largest daylight bombing raid attempted to date. Fighter escorts, P-47 Thunderbolts, would accompany the bombers to the German border, then turn back due to fuel limitations. The bombers would continue alone. German radar detected the formations at 10:15 hours. Luftwaffe fighters scrambled from bases across southern Germany. Focke-Wulf Fighter 190S and Messerschmitt Bf 109S, approximately 300 fighters total, climbed to intercept. Anti-aircraft batteries at Schweinfurt went to maximum alert. The battle began at 11:05 hours as fighters reached the bomber formations. Fighter 190S attacked head-on, targeting cockpits and engines. Bf 109S attacked from above and behind, firing cannons into vulnerable wing fuel tanks. B-17 gunners returned fire. The sky filled with tracer rounds, cannon shells and falling aircraft. Bombers began going down. Some exploded mid-air when fuel tanks ignited. Others, engines shot out, spiraled toward Earth trailing smoke. Parachutes blossomed as crews bailed out. Some chutes failed to open. Other crewmen were already dead. At 11:42 hours, the lead bombardier over Schweinfurt, looking through his Norden bomb sight, identified the target. Kogel Fischer factories were visible through gaps in smoke from anti-aircraft bursts. He called corrections. Bomb bay doors opened. The formation began its bombing run. German anti-aircraft fire intensified. 88mm flak guns filled the sky with exploding shells. Each burst created a lethal sphere of shrapnel 50 feet in diameter. Bombers flew through continuous explosions. Metal fragments punctured aluminum skin. Hydraulic lines severed. Control cables cut. Men died at their stations. The bombs fell at 11:46 hours. 500-pound high-explosive bombs. Incendiaries. Delayed action bombs. 230 aircraft dropping their loads simultaneously. The factories below disappeared beneath explosions and smoke. The bombers turned for home. German fighters pursued, attacking continuously. More B-17s fell, the formation thinned. By the time surviving bombers crossed back into Allied airspace at 15:20 hours, losses were catastrophic. 60 B-17s destroyed. 26% of the attacking force. Of 601 crewmen aboard those aircraft, 102 were killed, 381 captured, the remainder evaded, or were interned in neutral countries. German losses were also significant. 25 to 35 fighters destroyed. But Luftwaffe aircraft could be replaced within weeks. Trained bomber crews could not. The exchange rate favored Germany. But the bombing worked, temporarily. Post-raid reconnaissance showed extensive damage to Schweinfurt factories. Kogel Fischer's main production building was gutted. VKF plants suffered heavy damage. Fichtel and Sachs production lines were destroyed. German ball bearing production dropped from 140 tons in July to 69 tons in August to 50 tons in September. A 64% reduction. Albert Speer later testified that if the Allies had concentrated on ball bearing production, continuing raids would have crippled German war production within 4 months. But they did not continue. The losses were unsustainable. A second raid on October 14, 1943, Black Thursday, cost another 60 B-17s set out of 229 attacking. Loss rates exceeding 25% made deep penetration missions without fighter escort impossible. The raids stopped. Schweinfurt was not attacked again until February 1944, when P-51 Mustang fighters with drop tanks could escort bombers throughout the mission. By then German production had recovered. Factories dispersed to underground facilities and smaller shops. Stockpiles accumulated during the bombing pause sustained production. Germany also imported bearings from neutral Sweden and Switzerland. SKF's Swedish factories supplied approximately 10% of German needs throughout 1943 and 1944. Bearings were small, valuable, and easy to smuggle. British intelligence conducted covert operations to interdict these supplies, including dangerous flights by BOAC Mosquito aircraft to Sweden, returning loaded with bearings purchased by Allied agents. But enough got through to prevent collapse. Kassen 20 fork through to prevent collapse. German engineers also redesigned equipment to use plain bearings instead of ball bearings where possible. Plain bearings, simple bronze or steel bushings, require frequent maintenance and replacement but can be manufactured with basic machine tools and non-critical materials. Performance is inferior, but functionality is maintained. Post-war analysis concluded that the Schweinfurt raids, despite costing hundreds of American lives, achieved limited strategic effect. Ball bearing shortages never crippled German war production. By 1945, Germany had larger bearing reserves than in 1943, despite continued bombing. While B-17s spurned over Schweinfurt, American factories were solving the bearing problem differently. Not by destroying German production, but by producing alternatives that worked better. Timken's output during 1943 exceeded 200 million bearings. Production in 1944 exceeded 300 million. By war's end in 1945, cumulative production exceeded 1 billion bearings. The statistics reveal the scale. Every military vehicle, every aircraft, every ship, every piece of artillery, all used Timken bearings. The United States produced 297,000 aircraft during the war. Timken supplied bearings for landing gear, engines, and control systems. The United States produced 88,000 tanks and self-propelled guns. Timken supplied wheel bearings, track bearings, transmission bearings, and turret bearings. The advantage accumulated gradually. No single bearing prevented a defeat or ensured a victory. But across millions of vehicles, billions of operating hours, and 4 years of war, the cumulative advantage was decisive. Every bearing that did not fail meant one less vehicle disabled. Every vehicle operational meant supplies reached the front. Supplies at the front meant offensives continued. Continued offensives meant victory. German logistics officers understood this. Captured documents after the war revealed constant concerns about bearing supplies. Maintenance reports documented bearing failures, forcing equipment out of service. Procurement records showed desperate attempts to obtain bearings from any source, including stripping damaged vehicles for reusable bearings. American logistics officers did not share these concerns. Bearing supplies were abundant. Replacement bearings arrived faster than they could be installed. The question was never whether bearings were available, but how quickly they could be delivered to forward units. This logistical superiority, invisible to historians focused on battles and campaigns, fundamentally shaped the war's outcome. The physics Henry Timken exploited in 1898 remained unchanged in 1944. Line contact distributes loads better than point contact. Tapered geometry handles combined loads better than spherical geometry. Adjustable bearings adapt to wear better than fixed bearings. These principles, worked out in a St. Louis carriage shop, became the foundation for American military logistics in World War II. Henry Timken died in 1909, never knowing his invention would help win the greatest war in history. He simply wanted to build a better bearing for wagons. He succeeded beyond imagination. The immigrant from Bremstedt, Germany, who apprenticed as a carriage maker at 16, invented something of genuine value to the world, exactly as he intended. The tapered roller bearing reduced friction fundamentally. It still does. Modern heavy equipment overwhelmingly uses tapered roller bearings. Automotive wheel bearings in trucks and SUVs. Aerospace landing gear. Railroad freight car axles. Industrial machinery. Wind turbines. Mining equipment. Construction vehicles. All rely on the same tapered geometry Timken patented in 1898. And while American bombers died over Schweinfurt trying to destroy German ball bearing factories, American factories quietly produced something better. Not through dramatic raids or strategic bombing, but through patient engineering and mass production. The bearing war was won not in the skies over Bavaria, but in factories in Canton, Ohio, where a German-born inventor's design, perfected by his American company, rolled off production lines by the millions. America did not need German ball bearings in 1940, it had something superior, and that obscure mechanical advantage, unknown to most Americans then and forgotten by most historians now, helped win the war as surely as any bomber or battleship.